All right, we're going to continue our discussion on sample spaces and events. And what we want to look at is the OR. So I'm going to draw two outcome spaces here. Right? And so if this is all possible outcomes, I can have event A and event B, or event A and event B can do this. And so this visual representation of my sample space so these are two separate representations of sample spaces. And we have, let me get back here. Sorry, I'm traveling around here. Event A and event B, and event A and event B. These share no outcomes. There's no outcome common to these. Well, these have this overlapping space where outcomes are shared. So, for example, if we're looking at rolling dice and event A is rolling odds and event B is rolling evens, there is no overlap. If here, event A is rolling odds, and event B is rolling greater than 3, well, there is an overlap, because 5 is an odd greater than 3 that would be in this. And so we could say this would have the events 1, 3, have the outcomes 1, 3, and 5. This would have the outcomes 2, 4, and 6, and there's nothing shared. Well, here, this would have 1, 3, and 5, and this one would have 4, 5, and 6, and they share 5. And so these are called mutually exclusive events when there is no overlap in the outcomes between the events. And for the wonderful word, these are not mutually exclusive. And so we want to kind of think of the probabilities. And so we have a rule. And in this case, when we're trying to figure out the probability of two either or events happening, this isn't an and. This is not one event then the other. This is either A or B. Visually, what we want to think of is if this is all of the outcomes, and I'm thinking of the area I cover by these things, well, I have to add the areas, right? It doesn't increase the outcomes like one event after the other does, but it does change the amount of space that is covered by the outcomes. And so mutually exclusive, the probability of A or B happening, when they're mutually exclusive, is the probability of A and B added together. And so the probability of rolling an odd is 1/2, and the probability of rolling an even is 1/2. And so the probability of rolling an odd or an even is 1. And if you think about it for a second, 1 being 100% or guaranteed, when you roll a die, you're always going to get an odd or an even, hopefully. In this case, though, the probability of A or B when they're not mutually exclusive updates the formula. We have to take into account that shared space. And so we say it's the probability of A plus the probability of B minus, and we have to subtract from it that shared amount. And that shared amount is the probability of A and B. And so in this case, it's 1/2 plus 1, let's see if I get it right, half minus 1/6 or 5/6. And if we count all the things, there's 1, 2, 3, 4. What did I miss? I missed the number 2 over there. Sorry about that. There's 3 things there and 2 things there. And so the probability of rolling an A or B is 5/6. Alright, so sorry, my email beeped at me and changed my screen on me here. And now I've got jumpy screen. There we go. Sorry, some of my controls are off screen here. And when things happen, it sometimes makes me move things around. But let's realign this up and through. And so that's the addition rule. I want to give an example of mutually exclusive events. But I think I'm going to jump right to a summary of probability. We'll do some examples as we work on homework problems. Homework is a good place to do examples, right? Lecture, you kind of talk about theory, and then we work on the examples, and we're setting up the rules. So let's come here. See if this still, yeah, it did. All right, good. So we have these different types of probabilities. And so we have the classical probability, which gave us the number of outcomes in the sample space is known, like a die, and the outcome is equally likely to occur. And then the probability of an event is the number of outcomes in the event divided by the sample space. Empirical probability, we run an experiment, and the frequency distribution of the event that we want determines a probability. Now, probabilities are trapped between 0, meaning they can't happen, and 1, they're guaranteed to happen. We have complementary events, which are events not part of our event. And so it's 1 minus our event. And of course, the probability of the event is 1 minus its complement. And then we have the multiplication rule and the addition rule, that we can, if event A happens and then event B follows, if they're dependent, we multiply the probability of A times the probability of B given A happens. If they're independent, we multiply the two probabilities. Notice multiplications really increase the outcome space. These denominators get large because of the multiplications. While an addition rule, which is an OR, the probability of A or B happening, is we add the probabilities if they're mutually exclusive. If they are not mutually exclusive, we add the probability of A and B, and we subtract from it the part that overlaps. All right, that's a summary of probability, and we're going to work on some more examples. I'll find a way to kill the email incoming sound, but we'll work on some more examples as we work our way through.